Any other questions before we get going? Multi-step synthesis will be on the test. We don't really have a lot of time to spend here. I can send out answer key to this, or I may actually create a video. Is there one in particular you'd like to do, or any questions about multi-step synthesis? How are we doing with these? Second one there. I have a synthesis of the second one.
Nitro.
3-iodoaniline. Meta-iodoaniline. Hey, I thought it said 3-iodoaniline. Somebody have a synthesis of that compound?
HNO3 and H2SO4, put nitro on it first. And then you
You want to iodinate first?
no, like
If
you
you iodinate first, that's an ortho-pair director. Once you put the iodine on, you're not going to be putting anything meta.
put a nitro on first.
Nitro.
Put the nitro on first. Then iodinate,
And then reduce.
then reduce the nitro to the amino. Okay? Precursor. Precursor is a meta director. Do you want to brominate first and then put something on? No, bromine's ortho-pair director. Well, that's an ortho-pair director. What's precursor here?
Whatever it's called.
Precursor to an alkyl group would be a acyl group. We can acylate, that's a meta director, then brominate, then reduce the acyl. Clemmensen reduction, hydrogenation, or what? Wolff-Kishner, which is hydrazine and hydroxide. How we do on these down here? This is some review of organic, test one material. Yeah, how do you make ethers? I'm just going to put this group on. You also cannot do just one step Friedel-Crafts alkylation. We're not going to back this up and say, hey, we're going to react this with not that anyway. That there, aluminum trichloride, Friedel-Crafts alkylation. Such is not permissible. We need to remember test one material, ether. How do you make ethers?
Breaker ring.
I would back this up to this alcohol. If you had that alcohol, could you make that ether? How would you do that? Maybe sodium followed by what? Ethyl bromide or iodide? Yeah? Okay, how do you make the alcohol? Carbon-carbon OH, nucleophile carbon-carbon OH. Back this up to Grignard plus that epoxide. Would those react to give this alcohol after appropriate aqueous workup? Yeah? How do you make Grignard?
You could bromate the benzene.
You take bromobenzene and react it with magnesium. And then how do you make bromobenzene if you were asked to start with benzene?
BR2 and FeBr2.
BR2 and a Fe or FeBr3. How we doing that one? Question?
So should we just assume like we're not allowed to use Frito-Crafts like at any point? Like for example, if we didn't use that coal molecule, or like, for example, like that salt.
You can use Frito-Crafts, but it has to be simple. You can't put this huge big side chain on with a single reaction. All right, this I can't allow you to do. We need to build the molecule. Frito-Crafts needs to be, if you're going to use Frito-Crafts, it just needs to be plain alkyl or an acyl. Okay. To put all this on, one step, hey, I'm done. Can't allow you to do that because you need to go through multi-step synthesis. Really cheating. So then, make anything but a side chain, just do, I'm just going to one step Frito-Crafts. Okay, we need to look at the yellow handout. All right. At this point, we're going to look back at substituting a leaving group on the benzene ring. A traditional leaving group. In an EAS reaction, what is replaced on the ring?
Hydrogen.
When we take benzene and we brominate it, what is replaced on the ring? Hydrogen. That's a substitution reaction, but we're substituting a hydrogen, replacing a hydrogen. That's not a traditional leaving group if you think about SN1, SN2 type chemistry, E1, E2. Yes, it left, it's gone, but it ain't doing leaving group like, it's not becoming minus, it's not taking a lone pair with it. It actually is leaving the electrons behind, it's leaving as H+. Not a traditional leaving group. Can we do traditional leaving group chemistry with aromatics? Something like a chlorine or bromine or something. Yes, you can. There's some warm up here. So substitution of a leaving group, more of a traditional leaving group by a nucleophile. And we're using here nucleophiles to substitute a traditional leaving group. Okay? And if that's a nucleophile, the ring must thus be the electrophile. And we can replace the leaving group with a nucleophile. Just like in SN2, you replace the leaving group with a nucleophile. But this ain't SN2 or SN1 because neither of those mechanisms can you do here because the leaving group is not on a tetrahedral carbon. Leaving group has to be on tetrahedral carbon to do these mechanisms. Well, it's not EAS because the ring is reacting with a nucleophile. In an EAS, the ring reacts with what? An electrophile, a more positive species, like an I+, or it doesn't have to be exactly positive, it's electron-poor species. The mechanism here is either NAS, simply nucleophilic aromatic substitution, as opposed to EAS, or Benzyne. There's two ways to do this, NAS or Benzyne mechanism. Let's look at NAS. Here's a model reaction. We take chlorobenzene with sodium methoxide with some heat, show this product. Now this is, of course, what? This is O-, yeah? O- would be a nucleophile. So this is certainly not EAS because we don't have an electrophile here. Let's do NAS. How can we replace this group? Could we come in here and, whoop, done?
No.
Well, no, because what I just did is SN2, backside attack, kick off, and we don't do SN2 here, right? So you would never just do that because we already said we don't do that. What about if this leaves and make cation, and then we come in? No, because that would be SN1. And we don't do SN1. So we got to do this some other way. Well, here we go. This does react here. We do have dipole. There's some partial positives here. These electrons add here, but instead of kicking off the leaving group directly, what do?
Do you add at the same time?
I want to draw these pi bonds in a little better. Yeah.
It adds to the same.
Like it adds to the same carbon?
Do what?
Adds to the same carbon as the chlorine and they're both on there like together at the same time?
Hold
Let's do
on.
lone pairs on the adjacent.
Hold on. You want to do a chlorine and an OMe here?
Well, the pi bond would
That's
be,
5 bonds of carbon.
the pi bond would be broken.
Pi bond goes.
It goes on to,
The answer here is instead of breaking the sigma bond to the chlorine, we break the pi bond to the carbon. We've done this before. When we add, we're going to break the weaker bond. We did this before a couple of times, like when we made tosyl chloride, tosylates. Okay? And that gives what? Yes, they're both bonded there. Boom, boom. But right here we have what?
negative charge.
A lone pair that came from moving the pi bond. Okay? I had to redraw that in, but pi bond. Either one can be considered the pi bond. Okay? And that's a minus charge. And we're going to call this nucleophilic addition. Now, this no longer aromatic because we have a tetrahedral carbon now. No longer aromatic. But it is resonance stabilized. We can do resonance. These electrons move here. These electrons move out. These electrons move here. These electrons move out. Note that here the ring takes on a minus charge. In an EAS mechanism, the ring takes on what charge? Positive. Okay? Because there it's reacting with a, like an I positive. It's reacting with a electrophile. The electrons are attacking something that way, leaving a positive here. Here, electrons are coming in from the nucleophile. Anion. It is resonance stabilized. That was step one. The next step is just to come back. I'm going to change colors. You may not be able to do that. Yes, the resonance is there. There's your one intermediate, right? That's one thing right there. You can draw a hybrid. But the next step is the electrons just come right back, and anytime you can make a pi bond and kick off a leaving group, that's easy to do. Which is a better leaving group here? Chlorine. And when we do that, what do we get? There you go, there's your product. And what do you want to call that step? The first step was nucleophilic addition. What's the next step? Elimination. We've done this before. NAS is essentially an addition-elimination mechanism. The nucleophilic addition is going to be the rate-determining step to make the high-energy intermediate. Then when you come back in and remake the pi bond and expel a leaving group, we go back downhill to a neutral product, and that's going to be a fast step. Which step does the leaving group leave in? The rate determining step or the fast step? Clearly, it's the fast step. Which step does the leaving group leave in SN1 or SN2? Rate determining step, SN1, SN2. In this mechanism, the leaving group leaves in the fast step. Because of that, we will see you don't have restrictive leaving group requirements. If the leaving group leaves in the fast step, it's much easier for the leaving group to leave. We may see some strange leaving groups here. You're like, well, can that be a leaving group? And I'll say, if it's a fast step, it can be. It would never leave in a rate determining step, such as SN1 or SN2. Addition, it is resonance stabilized. Elimination. This is an NAS. Okay, unfortunately I've lied to you here. This reaction as written does not take place. Seems like a reasonable mechanism. I'm telling you it does not take place. What does that sort of imply? Why would this reaction not take place?
It has its requirements.
Because it's too difficult. That's why it wouldn't take place.
Does it need more heat?
Reactions that are too difficult don't take place. Why is this reaction too difficult? Apparently, the rate determining step is too difficult. Why?
We need another director on it.
Let's do a reaction coordinate diagram for this reaction. Okay? Let's go A, B, there's our intermediate, C, product. Some arbitrary level here, A. Where's B? B, and then we'll come back down. I'm not going to try to distinguish, I'm just going to say C. Okay? Here's our nucleophilic addition. And the next step is easy. We're falling downhill. Doesn't take much. Boop. There you go. Expel the leaving group. Right? Why would this reaction not take place? Apparently what?
Needs more heat.
These questions may be too easy. You can't. It's too easy. That's why you can't come up with the answer. Why does this reaction not take place? Apparently the energy of B is too high, and we can't get up there. That's what I'm trying to get at. That's why a reaction would not take place. The thing you're trying to form is just too hard to form.
So if you add more heat to the system, will it be easier?
I did say mild heat. Maybe you saw that.
We need more directing groups to stabilize the transition state.
Have you been reading?
Oh, just introduction.
Okay, read ahead. Here's the thing. This reaction doesn't take place as shown, mainly because apparently B is just too high. Even though it's resonance stabilized, it's still hard to do. We are breaking the aromaticity. This is aromatic. Not only is this an anion now, it's also not aromatic. So the difference here is, even though it's resonance stabilized. Okay. It turns out you need a withdrawing group on the ring. And it needs to, you need more resonance. How can you stabilize this further? How can you stabilize B further?
Nitro group.
More resonance. How do we get more resonance? We need a group where the anion falls, either ortho, para, or ortho. Ortho or para to the leaving group. We need a group that we can do resonance. Let's add one. What about a carbonyl? Let's add that in each structure. Same place. A methyl ketone. Now the reaction will work. Why? Because we have stabilized the intermediate. And now it will apparently work. Or it does work. Apparently the reason because can we illustrate the extra stabilization? Yes. We can draw an additional resonance structure right here. These electrons we can move here, that way. But we can also move these electrons in here and these out. And that will give, I'll draw it over there. We have double bond, double bond. But now we have boom. And this is also important. Is that the right resonance structure? Electrons into carbon, electrons out onto oxygen, yeah? Boom, double bond here, electrons out. Okay? We have an additional resonance structure stabilizing the anion. But here's the important place. Where have we now put the anion? Over here it was on carbon, carbon, and carbon. But in our additional resonance structure, it's on oxygen. Even more, even something even better. Additional resonance structure, yes, but now it's on oxygen, which is a major resonance structure of my 4. Negative on oxygen. Very important. The reaction will take place now. NAS has a requirement. Requirement. Strong electron withdrawing group. Where? It has to be
Ortho or para to the
ortho or para to leaving group. What if we had put the ketone group meta to the leaving group? we would not have been able to draw the additional resonance structure. Because the minus would have to fall there to be able to move it in here. The minus only falls ortho to the leaving group, or para. And so that's where the group has to be. Requirements: strong electron withdrawing group, ortho para to leaving group. And the electron withdrawing group typically needs to be able to do resonance. Rate determining step. We already talked about that. Leaving groups. Leaving groups. Many can leave. Somebody will say, can that leave? Is that a leaving group? I'll say what? Yes, if it's a fast step. Remember, the leaving group's leaving the fast step here. Expelling that leaving group. Okay, this is NAS. It's a very common reaction. It has a requirement though. Example. Take this compound. You could react it with sodium sulfide or sodium hydrogen sulfide, and we can replace the F. The F is the leaving group. Does the F have a strong electron withdrawing group, ortho or para?
Yes.
Yes. In my example, I used a carbonyl as the electron withdrawing group. Nitro is very common. Okay? And you should practice drawing resonance structures into the nitro group. Right? The nitro has basically, like the C double bond O, you do resonance here. It also has that. But you should look at the structure and be able to draw resonance structures with nitro. Very common. But hold on. Is F a good leaving group? We never used F as a leaving group for SN2.
It's leaving it at that step, so it's, yeah.
Right. You would never do F. Well, never say never. But we basically said F is the lousy leaving group for SN2, right? Yeah, because that's a rate determining step. But here it's actually, F is actually better than iodine for this.
Because it's happy being negative.
And let's explain why.
Because it's really electronegative, so it's happy being negative.
Well, no, that's not really the reason. If that was, that argument sounds like it should be a good leaving group for SN2. Because it is, it's happy being minus. But it's not the best leaving group for SN2. Something else going on. Got to remember, when we say it's a better leaving group, that means the reaction is easier. Well, which step is influenced to make the reaction easier? The rate determining step. Does the leaving group leave in the rate determining step? No. So how can it affect the reaction if it's not even leaving? Well, what is the first step? This coming in here. What would make this more easier to come in there? The more partial plus you have here, the easier it is for this to attract and come in there. Which is going to give you more partial plus here? F or iodine? Well, that's just electronegativity. F is more electronegative. The reason it's a better leaving group is not so much because it's leaving, it's because it generates more partial plus here. And it makes this first step, which is the rate determining step, the nucleophile coming in, makes that easier. Or more likely to happen because you have more of a plus. Yeah.
Say you don't have any electron withdrawing substituents on your ring, and you react it, but you complex it with magnesium to stabilize the transition state. Would that work?
Complex what would?
The intermediate with the...
Oh, the anion?
Yes.
I mean, perhaps, that seems reasonable. Just have to find an example of that if it's really known. Okay, so actually F is the best leaving group for NAS because it makes the carbon there more partial positive. And it gets the nucleophile to come in. All right?
And you can actually look up the Sanger reagent.
I looked that up on the wiki. It's used for labeling, I think, amino acids or something in biochemistry. But it has it's doing an NAS and it's kicking off a fluorine. Okay?
What we got next? Ammonia, be a nucleophile, right? Wow. We got a bromine, a chlorine.
Cyano group. That's an electron withdrawing group. You can do resonance. You should see that and do that.
Which halogen are we going to kick off? I've already given you a product. Which halogen has a strong electron withdrawing group, ortho or para?
Chlorine.
Chlorine. Not this. These are meta to the bromine. This one has two groups, ortho and para. Mechanism comes in, makes anion, resonance. You're going to be able to stabilize that anion by resonance into both groups. That's the leaving group we're going to displace by NAS. Now this is a neutral nucleophile. It's going to have to lose an H to go neutral here. What can take the H? Well, the leaving group. You're going to generate HCl. Now, that's not good. You probably need two equivalents here of ammonia. And the other equivalent of ammonia will react to make ammonium chloride over there. Because if you only use one equivalent, the reaction is only going to go halfway. Because once you start making HCl, the ammonia will no longer react here. It'll just react with the HCl. So you're going to be careful if you're generating acid and you have a base. The generated acid will destroy your base, your nucleophile. But one way to get around that is to use two equivalents of the nucleophile. Okay? By the way, is the cyano group an activating group or a deactivating?
Deactivating. Or it's a
Is the
group,
cyano group an activating group or a deactivating
it's a
group?
group 4.
Deactivating AES.
Because here,
For EAS.
the cyano group made this reaction happen. The cyano groups activated this chlorine for substitution. Hold on, cyano group's a deactivator.
It just depends on the reaction.
Depends on the reaction. Cyano group is a deactivator for EAS. Nitro group. Is a nitro group an activator or a deactivator?
Deactivator, ordinarily.
If it's a deactivator, what happened up top? Because I would like to say that the nitro group activated the fluorine for being displaced.
right? Because if the nitro group wasn't there, you would not be doing that reaction. So is everybody with me that the nitro group activated the fluorine for substitution? But I thought it was a deactivator. But what I'm trying to get at is, whenever you hear activator, deactivator, you got to know what mechanism you're talking about. Traditionally, that's EAS terminology. But I often hear, and I would say here, that the nitro group is activating the fluorine for substitution. So don't confuse those terms. How about down here? Product. Why don't you do that one on your own, and we'll look at these down here. You can do that one on your own. How about the next one?
No reaction.
Oh, this is O minus, right? What we got here?
Something that's withdrawing group that's meta.
Can you do NAS here? What does NAS require?
Ortho para with active. Energy with
No reaction. Certainly no NAS. Because the chlorine does not have an electron withdrawing group, ortho or para. By the way, back on through our leaving groups. Many leaving groups. Oxygen, neutral oxygens. You may even see a carbon as a leaving group in an NAS. You'll see many things. If you've ever seen it be minus, it can be a leaving group in NAS. All right? But not there, because we have a requirement. Okay. It could be benzyne. Let's look at the next mechanism. Benzine mechanism occurs when no strong electron withdrawing group is ortho-paired or leaving group. Or can occur. That might be a little bit better. It's a mechanism that can occur when no strong. Okay? But it requires harsher conditions than NAS. Or a very strong nucleophile. Very strong. Some of them very strong. And importantly, with benzyne, isomers are possible. You take chlorobenzene. And try to react it with KOH. At room temperature, there'll be no reaction. However, if you take KOH and react it with chlorobenzene at like 300 degrees and apply some pressure, like 2,500 psi, it's pretty high pressure, we can get a reaction. Now, you will have to have acid workup. That's just to put the proton. And we can replace the chlorine with the nucleophile. This is called sort of harsh conditions. Okay? Pressing, harsh conditions. We're going to force these things together and do something. Okay? We know you don't like to react, but we're going to force you to. Forcing condition. Mechanism. Is the hydroxide going to come in here and create an anion?
like we did with NAS? The answer is no. We're not going to do that NAS addition. You only can do that, what I did originally. If there's no electron withdrawing group ortho pair, you're not going to do that mechanism. So we would never do that here. We also know we're not going to just SN2 it off. We're not going to E2. What else can we do? Well, here's the other thing we can do. Hydroxide can take an H. How acidic is this hydrogen? Not that acidic. Not that acidic. Is there anything that is making that H acidic at all?
Resonance stability.
Of this? There's no resonance there. Thank you for saying that. We've got to make sure. That is not resonance stabilized. You cannot show resonance structure there. No resonance there. Make sure you understand. We do have dipole. Okay? There is something we can say here, is at least that anion is on an sp2 carbon. And remember alkynes? These have some acidity. Why? Because the H is on a
Triple bond.
sp carbon. And we always said that this is the only time we're going to remove like a hydrocarbon H. It's the main time. Well, here we're doing it on an sp2. But guess what? It takes pretty harsh conditions. All right, 300 degrees. That's high pressure. You're forcing these things to come together. All right, very high energy. See, this is something that's very high energy, but we're doing it we're putting in high energy. Someone said, can you heat it more? But this is what you get. Now this, all right, now this is often the rate determining step. Okay? But I'm going to say usually, because the rate determining step can actually vary in this mechanism. From here, these electrons can come here and kick that off. And that leads to what? A triple bond there. And what do you call it? What do you call this functional group? Alkyne. This is called a what? Benzyne. Now someone I think said, ooh, what do you not like about that?
Very unstable.
Why?
It's a bond that wants to be linear that's at an angle.
Very good. Linear. This is linear. 180. Is that linear?
No.
Each carbon. I mean, is that carbon linear? No. Triple bond would be like that. Yes. We can talk about that. Let's get through it today here. That's a benzyne. Very reactive. At this point, your nucleophile, which you can either use excess, but how does this exist right now? Water. Very reactive. This can come in and move the electrons back. By the way, the first here is elimination. I showed it as a two-step process. Elimination first, followed by what? Nucleophilic addition. So it's the opposite. Benzyne is often called elimination addition. And what does that give? Water now here, that's a positive charge. What's now on this carbon again? Anion. What's going to happen to this?
Intramolecular.
That's dying for a proton transfer. This needs an H to go neutral. That needs to lose a proton to go neutral. This is just going to be H plus transfer. And what do we get? There's an H here now. But the reaction's not over. Because the reaction was under basic conditions. There's base here. This is acidic. With base, this is going to be deprotonated. Because phenols are going to be deprotonated by hydroxide. And this is the end of the reaction right there. It's going to exist there.
So is that why we need to work up?
That's why we need the H plus workup. You got to put the proton back on. Phenols are acidic. If you make an acidic compound under basic conditions, how are they going to exist? In the basic form. Many years ago, somebody made up a stupid analogy. If you knit a sweater in the pool, the sweater will be wet when you get done. You will then have to dry your sweater. Okay? If you make an acidic compound under basic conditions, your product's going to exist in the basic form. You're then going to have to put the proton back on. Okay? And yes, how many equivalents of KOH do you need here? 2 equivalents. 1 to react and 1 to deprotonate. If you only use 1 equivalent, the reaction will only go halfway. Because as soon as it takes place here, the hydroxide will see the product and go, whoo, proton. Hydroxide will come over here, and you won't have enough hydroxide to do your reaction. But you need 2 equivalents. That's analogous to what we said earlier with the ammonia, how we needed 2 equivalents. Okay, we're about out of time. This is called a elimination addition. Benzine mechanism. There's some speculation about this. There's a couple of things we can add. This was proven. For a long time, some chemists thought, this is BS. I mean, I don't believe this. There were some classical experiments that helped prove this. Okay, we can look at that. We'll finish things up on Wednesday. Probably most of the day on Wednesday. Friday, we need to start new material.